Hi, I'm Sarah. I took LinSig in fall of 2024, and this is a review slash summary of signal basics. Let's start off by reviewing just what a signal is. Signals essentially are the action of taking an input into this black box and getting the output. And they're generally there as a function of time. So the signal that you get is the output you receive to an input that you put in this mysterious black box. In the real world, they have applications in things like neuroscience, where the brain responds to sensory inputs that we give it. Things like tuning forks, where if you strike one in an opera, it's going to reverberate in a certain way. And even cars going along a road and reacting to the different potholes and bumps in the street. There are two main kinds of signals. We're going to remember that they function as a function of time, so not of x as you might see in other places. It's an x of t instead of y of x. We have continuous signals. I'm going to write this in, continuous signals. And then we also have discrete signals. The discrete signals is compared to the continuous signals. Notice that instead of parentheses, discrete signals have brackets, and they're functions of n instead of functions of t. And that's how you can tell when you do calculations what kind of signal you're dealing with. The period of a function, the technical definition of it, is when f of t is equal to f of t plus some constant. Let's call it tau, because why not? So what this is essentially saying that at what point in time does the signal repeat? If we look at the signal that I have here, the sine function, you can see that it reaches a crest every 2 pi, or every 4 pi over 2. So t of my f of x here, or sorry, t of my x of t here is 2 pi. We can also define the frequency of a function as 1 over t. So in this case, we have 1 over 2 pi is the frequency of this function. There are mathematical relationships you can use to calculate the period for sine and cosine. So for sine and cosine, we have 2 pi over the absolute value of b, and b is whatever the sine of is being taken, the sine is being taken of without the t. So for example, if you have a sine of 2 pi t, you would be plugging this in for b. And then for tangent, it's just pi over b. That's how you calculate it. We also have even and odd functions. If you get an even function like cosine and you evaluate cosine of a negative value of t, you're going to get the same thing as cosine of t. For example, here on the graph, you can see that if we evaluate at point A, the y-axis value that we get is the same thing as it would have been if we evaluated at negative a. However, with odd functions like sine, there's actually some kind of mirroring effect, a reflection going on, where it's not directly even. Instead, sine of negative t is the same y value, the same output value, as negative sine of t. And you can see here that if we pick a point B here, and then negative b, they're actually, one's a negative version of the other, so this checks out. If you get two different signals and one is even and the other one is even, and you multiply them, you're going to get an even function back. If you get two odd signals and multiply them, you're also going to get an even function. But if you get an even signal and multiply it by an odd signal, you're going to get an odd signal in response. Let's go ahead and do some practice problems with this in mind. So we have the sine of 6 pi of t. Here we have our b, and remember that the formula for t is 2 pi over the absolute value of b. Here if we look, we have 2 pi over 6 pi. The pi's cancel out, you end up with 1/3 as your t. And then if we're getting our frequency, or our base frequency, we're going to get 1 over t, or f naught, and that's 1 over 1 over 3, which just equals 3. I want you to notice too that this is in the continuous domain, as you can see by the parentheses here and the fact that we're using t and not n. Let's try another signal, cosine of 2t. Here again, we're in the continuous domain, as you can see by the parentheses and by the use of t instead of n. We have the same formula, so t equals 2 pi over b. Here there's no pi, but we see our b is just equal to 2. 2 pi over 2. Our period then is pi. And then our frequency, base frequency, is 1 over t, 1 over pi, and there we have it. Let's do another example. I want you to notice that this one is actually in discrete time, as you can see by the brackets and the use of n. So this one's discrete, not continuous. If we get our period again, we're going to do 2 pi over b, and in b here is 5 pi. We're going to get 2/5. But with discrete time, you're always moving by a whole number, by an integer. So for example, you're going to have a value at 1, at 2, so on and so forth. We're not going to have a value of 2/5. That's not a thing that happens in discrete time. So we have to figure out what the closest integer is that you can make with 2/5. A good baseline for this, you can multiply by the denominator, right? So, multiply that by 5, and we're going to get a period of 2. Then again, you're going to get your frequency, 1 over 2 in this case. Let's look at this one. The plus 1 here shifts the entire function up by 1. So it doesn't really affect what we're going to do to calculate the period. And that is supposed to have a t there. I apologize for that. We're going to get our period equals 2 pi over b. Our b here, our b here is 2 pi. So 2 pi over 2 pi equals 1. Base frequency, 1 over 1 equals 1. In this one, we have two signs put together to make up our signal. What we're going to do for this is we're going to get the individual periods and then calculate the least common multiple of those two periods. So we can get the period for this, 2 pi over b, and these are also supposed to have t's there. Sorry about that oversight. 2 pi over 4 pi becomes 1/2. And in this one, we're going to end up with t equals 2 pi over b, which is 2 pi. We're going to get 1. Now we're going to find the least common multiple of 1/2 and 1, which in this case is 1, very convenient. Then our frequency is also 1, because 1 over 1 is 1. Now we have cosine squared of 4n, and another way to write this, these are supposed to be brackets, right, because it's discrete time, not continuous time. We're going to get, it's the same thing as saying cosine of 4n, that is supposed to be a bracket, times cosine of 4n. We're going to find the least common multiple of these two functions, which is pretty nice because it's the same thing. We're going to get our period equals 2 pi over b. There's no pi here, so we're just going to do 2 pi over 4 equals pi over 2. But wait, this isn't a whole number. Pi is irrational. You can't multiply pi by anything to get it to equal a whole number. So this one's actually not periodic in the discrete domain. In discrete domain. Because you cannot get that period to be rational. Let's try another problem. Cosine of t squared. If you take a look here, we can see immediately that this is not going to repeat itself at any point. There's no such number other than 0 and 1 where t squared equals we had written it as t plus tau squared. You would, if you tried to simplify this, you would end up with t squared plus 2t tau plus tau squared. For getting the n and 2n as we had done with the formula that I left up here, right? This is what I'm looking at to get those numbers. If I were to try to take the cosine of t squared and match it up to the cosine of this whole train wreck squared plus tau squared, there's no value for tau that I could get other than 0 where it would be the same thing as just t squared. Therefore, it's not periodic. But now what if we multiplied it by pi? Is there any number where we can get cosine of t squared equal to cosine of pi t squared? If you look at the pi, if you look at this on a unit circle, right, it represents a semicircle. And if you multiply the semicircle, that pi, enough times, you're going to get back to where you started. So because of that pi, it actually is periodic. If we try to calculate the period here, we get 2 pi over b, which is pi, equals 2. Let's move on to our next example. Let's try another tricky example here. We have in the continuous domain, cosine of pi t squared. The funky thing about this one is that you're trying to get cosine of pi t squared to equal cosine of pi t plus this arbitrary period, basically, squared. And because it's in the continuous domain, there's no number here that we can get to have it equal this. So it's not going to be periodic. However, if we had the same problem in the discrete domain, and catch those brackets that I missed, we actually can have a period here. Because what this is saying is that pi is going to get multiplied by some whole number. So 1 pi would take you this far on the unit circle, right? It would get you around to the other opposite end. And then 2 pi would get you back to where you started. So there's going to be some value of n here, where it's going to be a multiple of 2, and it's going to get you back to where you began. So let's do our 2 pi over b. B is just pi. And t equals 2. F is 1/2. Right, moving on to our next example. Here we have in the continuous domain a non-periodic function, right? T just kind of looks like that on the graph if you were to plot it. Just plot it on your x and y, right? T and then t. And then you have something that is periodic. Because you're multiplying something that is not periodic by something that is periodic, you're going to get a function, a result, a signal that is not periodic. What about this? E to the I pi, if you saw it in the last video, can actually be written as cosine of pi plus I sine pi. And then we're going to bring down the sine to pi t. Now that I did this, this is just constant. So we're going to end up with cosine of pi, which is -1 plus 0, I that cancels out, times sine of 2 pi t, which is the same thing as negative sine of 2 pi t. And we can just, again, do t equals 2 pi over b, which in this case is 2 pi is 1, f naught equals 1. Let's do another one. Again, we're shifting up here, so we can actually ignore this constant on the outside. 2 pi, t equals 2 pi over b, which is just pi here. It's 2, and your base frequency is 1/2. Okay, let's keep going. We have a few more left. Here we have a cosine of two terms added together, and there's actually a trig identity, let me pull it up over here, that states that the cosine of two summations, so cosine x plus or minus y, is equal to cosine x cosine y. Am I going to spill into the next one? Let's drag it down to the bottom here. Plus sine x, or plus minus, in this case is plus, sine x sine y. So if we apply this to m of t, we're going to get cosine of pi over 4t, cosine of pi, right, because that's our y, and this is our x, plus, because we have a plus here, sine of pi over 4t, sine of pi. Now remember that if there were, hypothetically speaking, a t here, we would have to find the least common multiple of those two periods, but there isn't, so it's just a constant. In this case, the cosine of pi is negative 1, so we end up with negative cosine of pi over 4t, plus the sine of pi is 0, so this whole term goes away. And now we can just do our 2 pi over b, and b is pi over 4. Pi's cancel out. We end up with 2 times 4 equals 8 for our t. Then our f naught is 1 over 8. Cool. Now we do have this one, and this again touches upon an Euler identity from the last video. You can see that it's 1/2, and then we have this funky e to the j pi, this e to the negative j pi squared. There is an Euler identity that states that cosine of I theta is equal to the e to the I theta plus e to the negative I theta all over 2. And you can see here that we have the 2 for one of the two cosines, but we don't have it for another one. So we end up left with a 1/2, and then times the cosine of j or I, they mean the same thing, times pi. And there is no t in this problem, so it's just a constant. The period of the constant technically could be any number, right? Because it's just a constant. It could also be 0. As a result, it doesn't have a frequency. But now we did simplify that. For this last problem, if we take all these constants that we have, we don't care about it being shifted up or down, and we don't care about changes being made to the entirety of the sine term that we have, but we do care about this 3. So this is in the continuous domain, meaning that we can have a period that's not a whole number. We're going to get our t equals 2 pi over b, which is just 3, and that is that. And then our f is the inverse of that, so 3 over 2 pi. Cool. Let's take a look now at some especially cool signals that allow us to do some pretty funky things in LINSYG that you wouldn't see in other classes, which is why this class is so fun. You have something called the unit sample, also known as the delta function, and this function has a value of 1 when the thing inside of these brackets here is equal to 0, and only then. Everywhere else, it has a value of 0. Let's take to the graph here and see what that actually looks like. So we have, this is discrete, and when we're plotting in discrete, we plot with little dots. So we have a 0 here, a 0 here, 0, so on and so forth. And then at n equals 0, right at this line, it suddenly jumps up to 1, and now n is no longer 0, so we're going to go back down to 0. And you can do a little stick there to really show, to really show that one. That is our unit sample. Now, in the continuous time, you can't really describe it as a function because it's just that one loop. You'd get basically an infinite derivative there if you tried, and it's just going to look weird. So the way that we describe this is as the derivative, with respect to time, of the unit step. And if you were to plot this, we have our time axis here, and then our function axis up here. And in continuous time, we just plot the lines. 0, 0, it's 1, and then it's 0. And this technically isn't kosher for the class, but that's just an idea of what this would look like. So let's take a look at this mysterious unit step that we have over here and plug that in here. The unit step is equal to, again, we have 1. Whenever n, the thing inside the brackets here, is greater than or equal to 0, and it's 0 when n is less than 0. So what this looks like, we have n less than 0, and this is discrete, so we have nothing. And then at 0, again, it's going to jump up to 1. But now it's going to stay at 1 as we move forward towards infinity. Let's do this again, but for the continuous time. We're going to have it's 1 when t is greater than or equal to 0, and 0 when t is less than 0. So again, we have nothing, 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 and then we have, at t equals 0, we jump up to 1, and then we stay at 1. So it looks like this cool little box-like thing. We can also play around with these new unit steps and delta functions that we just learned. And we can see here that, let's start plotting these two. I'm going to start with the unit step of n in purple. And this is discrete, so it's 0, 0, 0, 0, 0, 0. And then at n equals 0, remember we get our first jump up. And then it's going to stay up because it's the unit step. And these are all going to have little pegs. And then I'm going to do unit step of n minus 1. And this is actually going to shift it to the right by 1 in this case, because there's a negative sign that's shifting right. To do a quick little proof of that, let's test it at n equals 0, which is normally when just the unit step would turn on, right? You're going to end up with unit step of -1, 0 minus 1. And now the n inside, our new little fake n, is negative, so it's actually going to be off. But then at n equals 1, we're going to have the unit step of 0, which is on. So this one's also going to be 0, 0, 0, 0. At 1, it's going to be 0, and then here, it's going to start turning on. Woo. If you try subtracting these, as we can see here with our little subtraction sign there, they're going to cancel out as of 1. So this whole thing is going to turn into 0. We're going to have a 0 here, and a 0 here, with just one little peg up. And if this looks familiar to you, you're right, because it's actually the delta function of n. And this is just a nifty little relationship to have on your cheat sheet for the exam too. Let's do this again, but we're going to do it with a different shift this time. Here it's going to be -4 instead of -1. So I'm going to start with the unit step of t in blue, and this is continuous this time. It's nothing, and then at 1, it starts, at 0, it starts jumping up to 1. And now we're going to have the unit step of t -4. Remember the -4, it's going to shift it to the right by 4. So nothing, 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 shift it right by 4, and now it jumps up. And if you subtract these two functions, 0 minus 0, and then we're going to have 1 minus 0, and now as of here we have 0 minus 0 again. So that's what you're going to end up with. It's called the box function. Let's try multiplying two unit step functions. We have the unit step of t minus 1, which I'm going to do in blue, and this is going to shift it right by 1. T minus 1, and this is continuous, times the unit function of negative t plus 2. We have a negative t, so it's hitting from this side instead of from the other side. It's coming in from the right. Let's test a few values to make sure that we're doing this right, because it's get a little bit weird. If we try t equals 0, we're going to get negative 0 plus 2, unit step of 2, of 2, so it's, oh my gosh, of 2, so it's going to be on. If we have t equals negative 1, so we're going the opposite direction, we're going to have unit step of negative negative 1, which is 1, plus 2 of 3, so it's going to be on. If we try the unit step of negative 2, we're going to get, unit step of 0, if we try t is negative 2, but then if we, so it's going to be on, but then if we do t equals 2, it's going to be, sorry, this is going to be of 4, not of 0, whoops, negative negative 2 plus 2 is 4, and then t of 2 is going to be unit step of 0, so it's going to be on, but then if we try t of 3, or t equals 3, our unit step is going to be of negative 1, so it's going to be off. So this is actually off coming in until we hit 2, which is when it turns on. Now we're going to keep going here. When we're multiplying the unit steps, we try to find the place where they're both on. So with subtraction, you're looking for when one is on and one is off, but with multiplication, you're looking for the segment that they're both on. So here we have our little box from 1 to 2. Okay, let's do a few more examples. 2 times the unit step of t. So remember that the unit step goes nothing, 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 and then it becomes 1 here. But since it's b multiplied by 2, we're going to actually make this 2, and then it's going to keep going on its merry little way. 3 times the unit step of t plus 3, here we have a plus, so we're shifting to the left this time. And you can do the proof for that if you want. And we're multiplying it by 3. So we're going to start it at negative 3, up by 3, and then it's going to go on its merry little way. We include the arrow on that side. And then finally, you can actually cut off different functions here. So almost like a piecewise situation. If we have e to the t, the general shape of that looks something like that, where it grows exponentially. Or actually, a little further, right? Then we have unit step of t minus 1, so we're going to start it shifting right 1. I'm going to start here at 1. It's going to be nothing, and then suddenly when we hit that point, we're going to jump to our exponent. So that's what it's going to look like. It's going to be a little funky. But that is a brief review, a brief summary of the basic idea of what a signal is for this class. I hope you enjoyed, and if you have any questions, as always, feel free to reach out. I'd love to hear from you. Thank you so much for watching.